Hello everyone, my name is Blake Armstrong and I have been a part of the Pawsey summer internship that ran from 2020 to 2021. For my research project, I have been working under the biomolecular modeling group at Curtin University under Professor Ricardo Mancera. I decided to pursue the Pawsey internship program because I am interested in the useful applications of computing, and specifically supercomputing, in investigating nanoscale chemical phenomena. That brings me into the work I have been doing throughout the internship. I have been evaluating the efficiency of GPU-accelerated molecular dynamics simulations of biomolecular phenomena. Specifically, I've been comparing the compute efficiencies of GPU and CPU-accelerated simulations using two of the fastest and most popular molecular dynamics software packages, AMBER and GROMACS. I used these software packages on standard lipid bilayer systems to investigate the effect of cryoprotective agents on dehydration during the cryopreservation of cells. On the screen here, I have rendered images of a membrane at 3 different stages of dehydration after the course of a 125 nanosecond long simulation. It is this fully hydrated system on the left that I have used as the controlled system for comparison between AMBER and GROMACS. This brings us to the compute comparison. The molecular dynamics packages GROMACS and AMBER are very commonly used in the field of biophysical macromolecular simulations. GROMACS is heavily dependent on CPU-based calculation for every step of the MD simulation, whereas AMBER was developed with GPU-accelerated calculation of primary interest. The astonishing increase in GPU performance over the past decades has made AMBER's GPU-accelerated program for molecular dynamics simulation of significant interest. I was able to test the efficiencies of the GPU and CPU-accelerated simulation engine from AMBER and the CPU and CPU-GPU hybrid accelerated simulation engine from GROMACS. The performance of CPU-only acceleration from AMBER and GROMACS is shown on the screen. The use of CPU-only acceleration is clearly done better by the GROMACS software, which makes sense considering AMBER is highly specified into GPU acceleration. In comparison to the performances obtained by GPU-accelerated AMBER and a CPU-GPU hybrid acceleration, the GPU version of AMBER far outshines every other combination tried. It was demonstrated that using a single GPU on a single node with the simulation engine from AMBER is over 3 times faster than running the CPU version of GROMACS at its most efficient at 4 nodes, and that the GROMACS CPU-GPU hybrid acceleration is twice as fast at 1 node compared to just CPU acceleration. Some interesting conclusions I was able to draw from this work is that the single GPU MD calculation has such a high performance that the interconnect between multiple GPUs does not keep up, such that multi-GPU MPI calculations see relatively little improvement in performance. The AMBER code focuses on the interconnect between GPUs within a node, so it would be cost-effective to create GPU-dense nodes and run independent simulations within a node. And, most importantly, for high efficiency, equilibration and production MD should be run as a single task using a single GPU with AMBER on the Topaz system. I'd like to thank the Pawsey Supercomputing Center for the opportunity to take part in this summer internship. I've learned a lot about the supercomputing centers at Pawsey, and it's definitely set me up for success in the future as I continue to use the systems. I've come across a lot of great people along the way, and I'd like to thank all of them. And I'd like to thank you for watching. Goodbye.